Okay, so we're going to look at limits. We'll review the concepts of limits, and then we'll look at the limit tests, which are really useful ways to demonstrate things about big O, omega, and theta. So first of all, a quick review of the definition of a limit. We're specifically looking at limits as a function approaches infinity. So kind of generically here, I'm using the function h, which is a function of a variable x. And we're looking at it, a function that's defined whenever x is past some constant k. Really the important point is that there's some initial point. After that initial point, the function is defined out through infinity. Okay, so for the rest of our discussion, this idea of k really won't be important. Just keep in mind it's continuously defined past some start point. So our notation is that we think of the limit of our function as x approaches infinity as being L if for all epsilon greater than 0, there's some m also greater than 0, such that the absolute value of our function minus L is less than epsilon whenever we're past some point m. So let's think about that as a function in our plane. So we've got our x-axis here. We've got this line that represents L. Okay, and the left side of our inequality, the value of function at some x minus L, is about being within some distance of this line. So I'm going to come back to that in just a second. I'm going to focus on our other important clause here when x is greater than m. So I'm going to draw some horizontal line that represents m. And we don't really care what happens before this, but we care about what happens after this. So again, this is m. Okay, so now I'm going to come back to this part, the inequality. So this is saying that the difference between the function and L is less than epsilon. So that means that our function out here, we don't know what its value is exactly, but we know that it is no more than epsilon above L and no more than epsilon below L. And because this is true for all epsilon, we can keep picking an epsilon that's closer and closer and closer to 0. So to simplify this, we can say that our function gets arbitrarily close to L as x approaches infinity. Okay. Let's take that back and look at our big O concepts. So assume that we know that we've got a limit as n approaches infinity of a ratio of two functions, our f function and our g function. So we're tying this back to the notation that we've already been using for big O. And in this case, we're going to first focus on limits that we know to be 0. So assume this is true. We've got two functions. We know that the limit of this ratio f of n over g of n is 0 as n approaches infinity. So if we know this is true, what can we say about the functions? Which one grows faster? So from your experience in calculus, you can pretty clearly say that g must grow faster than f. It's the denominator of the fraction is gradually eating away at the numerator until eventually it's insignificant. Okay, so our claim is that when we have this specific case where the limit of one function divided by another function is 0, our claim, and eventually if we prove it, it'll be a theorem, our claim is that f is in the big O of g. Okay. So once we've proven this, we can then use limit tests in order to demonstrate that one function is big O of another. Okay, so we're going to try and connect the notation that we just used for the definition of a limit to the notation that we're currently using for big O. Okay, so let's move on and use these two different definitions to prove that essentially these are equivalent things. So our proof. We'll start with the definition of a limit, and we'll also work with the terms from the definition of big O. So the definition of a limit is about some function h. It's a function of x. It'll be equal to L as x approaches infinity. So let's just translate that into the terms that we've been using for our big O notation. So we'll replace the variable x with the variable we've been using for big O, which is n. That represents our problem size typically. And we'll replace the function h with a function that's actually a fraction, that's a function f of n divided by g of n. So it's still a function of n, it's just got a numerator and denominator that are clearly separated out. And again, right now we're focused on a limit of 0. Okay, so again, we've just identified that L is going to be 0. Our overall function h gets replaced by this function of f and g, ratio of f and g, and our variable x was just replaced by the variable n. So again, all we've done is we've changed, we've picked a specific limit, and we've changed our variable, and we've changed our function. So continuing on, let's look at the other components of the definition of a limit. So it says for any epsilon greater than 0, there's an m greater than 0 such that the distance from L is less than epsilon whenever x is greater than m. Okay, so let's translate that into our definition for big O. So first of all, I'm going to look at the end of this and kind of focus on this idea of being past a certain point to the right on our number line on our x-axis. And I'm going to bring that back to the concept of being past kind of our initial point, our start point, n being n greater than n0. So I'm going to equate the variable n, the variable m in our definition of a limit to n0 in our definition of big O. Okay. Okay, the other component that we're updating is the idea of epsilon being greater than 0, and we're going to replace that with some c being greater than 0. So if you remember the definition of c from our definition of big O. Okay, so we've already kind of figured out the components of this. We'll take the absolute value of our function, which is f divided by g. We'll subtract off our L, which is 0, and we already know that we're substituting c for epsilon. Okay, so let's simplify this a little bit. So we'll drop the 0 term here, and that gives us the ratio will be less than c, and we can multiply through by g of n to get something that looks very, very familiar to us. So f of n is less than c times g of n. Okay, so big picture view, we've got this inequality. We've got a c greater than 0. So this essentially matches up with our definition of big O. So we've essentially proven that the definition of a limit, when that limit is equal to 0, corresponds to our definition of the big O notation. So this gives us a new way of demonstrating things about big O. We can show that the limit of one function divided by another, by the limit of f divided by g as n approaches infinity. If that limit happens to be 0, it basically proves that f is big O of g. Okay, so let's continue on with this. So we already know that the limit as n approaches infinity of f of n divided by g of n, if that's equal to 0, it proves something about big O. And we already know that we'd consider the g function to be growing faster if this limit's upheld, and if this limit's true. So let's do another claim. Let's claim that f is not in omega of g. Okay. So we've got our same kind of assumption about limits and the limit being 0, but now we're talking about the big omega, and we're claiming that f is not big omega of g. Okay, so how are we going to prove that? So instead of proving that it's not equal, let's make an assumption. Let's assume that f is in big omega, and then see if everything works out. What we're really going to be trying to do here is trying to do a proof by contradiction. We'll assume the opposite of this statement and demonstrate that can't be, that there's some contradiction. Okay? So let's proceed to the proof. So again, we're assuming that this limit is true. And now the statement that we're trying to contradict, our next assumption is that f is in big omega of g. So recall the definition of big omega is that the f function is greater than or equal to c times g of n for some c greater than 0 whenever n is greater than n0, whenever we're past our start point. Okay, so we'll change this around a little bit. We'll divide through both sides by g of n, and we'll end up with our ratio f of n over g of n is greater than or equal to c whenever n is greater than n0. But it's greater than c. And if you remember, our definition of big omega is that c has to be greater than 0, not equal to 0, but greater than 0. And our first assumption was that we have this particular limit. So we've already encountered our contradiction. So it contradicts our first assumption about the limit of this. Okay, so this assumption must be false. Okay, summarize our limit test. We actually get kind of two things out of this. So we can demonstrate the limit as n approaches infinity of f of n over g of n is 0. We've shown both that f is not omega of g and also that f is big O of g. So this leads us to a new type of notation, little o. So we say that f is little o of g when, for all values of c greater than 0 and n0 greater than 0, such that for all n's greater than n0, f of n is less than c of n, c times g of n. Oh gosh, okay. What this is really saying is that f is strictly below g of n. So this is a little bit different than what we see in the big O notation, where we've got a less than or equal to. Here it's a strict less than. So an easier way of saying this is that f becomes insignificant in relation to g as we approach infinity, which, as we've just seen, happens whenever we can show that the limit of f divided by g is 0 as n approaches infinity. Okay, so if we can demonstrate this limit, we can say that f is in the little o of g, and we know something about both big O and big omega. Okay, we've got another somewhat comparable definition for little omega. So assume that we know that the limit is not 0, but it's infinity. Which function grows faster? Well, we have to assume that f grows faster, right? From our experience with calculus, we know that somehow the numerator of this function is growing without bound and growing much faster than the denominator. So our claim, which will again become a theorem, is that when we have this particular limit, f is in big omega of g, and f is not in big O of g. Okay, so we could go through the proof, which would be very comparable to the proofs we've already done. Instead, we will just claim that this is a theorem, and we'll introduce a new notation for it. So our new notation is that f is in the little omega of g. Okay, so now we've got two different types of limit tests we can worry about. We can think about what happens if we can demonstrate that the limit of the ratio of two functions is 0, and what it means when the ratio of the two functions is infinity. Okay, so now let's think about limits and how they relate to big theta. So this time we'll consider what happens when the limit happens to be a constant k, when k is greater than 0, so some positive constant. So based on the definition of a limit at k, So we know that this, if we have a limit at k, that our function f is going to be less than or equal to k plus epsilon times g, which is basically saying that that basically aligns with our definition of big O. Okay. We've got some constant c times our function g. Also, based on the definition of a limit at a constant, we know that g is going to be less than or equal to our function f over k minus epsilon. And again, this is equivalent to our definition of big omega. We say that, kind of reading this backwards and doing the algebra, we could say that f is greater than or equal to k minus e times g of n, which aligns with our definition of big omega. Okay, so our theorem is that we would consider f to be in the big theta of g whenever we can demonstrate that our limit ends up being a constant. Okay, let's summarize these different limit tests. So we're going to look at these three different types of limits we might experience and think about what each one means. So the first one is if the limit of the ratio of functions happens to be 0, then we know two things. We would consider the f function to be in the big O of g, and we'd also consider it to not be in the big omega of g. Let's think about the second case we looked at when the limit is infinity. And in this case, we know that the f is not in big O of g, but it is in big omega of g. And then the third case was when the ratio happens to be some positive constant. And in this case, we know that f is in the big theta of g. Okay, we also introduced some new notations. So if you remember, going along with our first test, when the limit is 0, our new notation is little o. And we could say that our function f grows slower than g. Our second limit was when the limit is infinity, and our notation for that was little omega. And we could say that f grows faster than g. Okay. And our third notation is when our limit happens to be some constant. And we didn't introduce new notation for that, it's just still big theta. And we could basically say that these two functions grow at the same rate. Okay, all of these different statements about the rate of growth are all asymptotic statements. We're all kind of talking about the rate of growth and the limit.